हो सकता है कुछ चीजें समझ में ना आए, but still I would recommend.
जी भाई साहब, देख मैं कर लूंगा, मैं देख लूंगा।
ठीक, sure. Okay, so let's continue. So last time we talked about. So these are the details of sessions, right? In session 1, we talked about the basics, first basics and stats, like the applications in real life, data representations, bar charts, graphs, histograms, and all. In session 2, we covered the center and the spread of the data. So in the center and spread of the data, we covered median, mean, and IQR. IQR is interquartile range. Standard deviation is also used for spread of the data. Then we covered Z score. I gave an exercise as well for Z score. In session 3, we covered the basics of probability. We started with the history of probability, random experiment, elementary outcome, sample space. These were the technical terms used in probability. Then we covered the classical probability, objectivist, Bayesian, relative frequencies, and all. Then we saw what are the events or not, and events. What are the mutually exhaustive events, basically, which have no common thing between them. Then we introduced the conditional probability. In the last session, session 4, we finished the conditional probability and started with the random variables. So in this we covered independent events, mean and variance of random variables, probability distribution, and we introduced the random variables, continuous random variables. So we'll continue. We'll continue with this session 5. So in a nutshell, what we covered in the last session was these rules. Basically, we saw that all these mathematical representations for let's say the probability of E or F, basically event E or event F happening together is probability of E. PE stands for probability of E. PE plus PF minus PE and F, basically E and F occurring together. It's so similarly we saw if the mutants are mutually exclusive, the C and F will be 0, and so it reduces to PE or F equals P plus PF, and then so on. Subtraction rule, multiplication rule. PE and F is going to be PE given F has happened into P of F, P of F probability of F. And then again, this will reduce if they are independent. The P of E given F has happened would reduce to probability of E. So PE and F will become PE into PF. So then we moved on to mean of the random variables, right? And we saw that mu is the symbol we usually use for mean calculation. And mu is calculated as sigma x px. So this x px means x into px for all x. Basically, whatever my x is, and x are the values of the random variable capital X, right? So capital X is the random variable. And we also call this as expected value of X or E capital X, right? This is the expectation that we'll use in the later sessions. Now, we also saw what was the variance for this, for the random variable and the values of the random variable. So they were, since we are dealing with samples only, so we have the variance, which is S square, is 1 upon n minus 1 into sigma of xi minus x bar plus square, where I varies from 1 to n, basically all your random variable values. And similarly, we could take it inside, and if the relative frequency is nx, we could multiply it with nx. So and then we so this was the last slide that we discussed about the continuous random variables, right? So again, I will reiterate. Let's imagine a random experiment for. I will repeat it for Jatin. So a random experiment is a one in which we are measuring an event, the probability of any event. Okay. For example, if we are tossing a coin, that is a random experiment that we are doing. Okay. And the results, let's say I define my event X as getting a head. right? So my event is getting ahead, and all outcomes will have some probability. So basically, having x is equal to 0, there will be some probability, x is equal to 1, there will be some probability, and so on. Now, for continuous random variables, it is a little different, because in this, all the outcomes will have a probability of 0. We will see how, we will see the examples and all, but the individual probability of any particular outcome is always 0 for a continuous random variable. Right. So, as an example, let's think of a spinning pointer. Okay. Think of it as a lattu. Okay, that we are spinning, and we are trying to we are landing it on a circular surface. Basically, this one. Okay, this animal that you see. Imagine it as a pointer. Okay, you are spinning it, and uh, once it lands, right, it can land anywhere on the circle. You don't have any defined point, and you are defining the random variable x as the proportion of the total circumference it lands on. Let's say it lands here, right? So it will touch the circumference at only one point, right? Maybe 2.3, maybe, I mean, a number of points it will touch, but that will range from 0 to infinity, right? So that is what we call a continuous random variable, right? So let's see. Let's talk about some distributions that we use in mathematical formulations and stats. So this is the top view of the same experiment, the pointer, and let's say after we spin it, it lands here, somewhere here at x. So uh, once we repeat it, right, it can land anywhere. Okay, so that's the reason we are saying that probability of landing at a particular point, we call it as 0. But as far as probability of landing in a particular area is concerned, we can define it. Let's see how. So some probabilities are usually easy to define. Okay, if I say that what is the probability that this pointer is going to land in the upper half of the circle, right? So by intuition, we can say that this is going to be half, because it has uh, the full probability of landing inside the circle is 1. So obviously the half area, the probability would be half, right? So that is what we can do with conditional um, continuous random variables, and we can define the probability for a range. For example, in this, if you say that the probability of landing between 0.25 and 0.75, then we can call it as 0.5. Why? Because we see that it's exactly half, right? So that's why we can call it as 1.5. Now, the random variable, which is x, right, it can take an infinite number of values. It can be, let's say, 0 to 1, it can be any value. It can be 0.001, 0.2144, something like that. It can be an infinite number. So all of these are going to be equally likely. We don't have any bias, okay? And all the random variable values are going to be equally likely. The probability of getting exactly 0.5 is going to be 0. So this will be true for any number, any value of random variable x. Okay. Uh, let's see how we represent them in more mathematical terms. Now we have a graph, okay, where on the x-axis I have all the values of the random variable. Okay, the values would vary from 0 to 1, right? And we have a probability distribution, right? So okay, taking a step back, let's try to draw a picture of all of this. Okay, this spinning experiment, let's try to draw a picture of it. Okay, now if this was the case with discrete probabilities, right, we would try to see the continuous probabilities as areas under something. because in case of discrete probabilities, we could define it with a number. Let's say number of heads coming up, it's 0.25 or something like that. But we can't do it for continuous random variables. So what we do is we define the areas under something. Okay, and okay, let's take this as a reference graph. Okay, from this graph, what I see is fx will be 0 when x less than 0. Fx is the area under the graph. Okay, so clearly, I mean, the value cannot be lesser than 0, right? The point where which it lands, it cannot be lesser than 0 because the points which are available are 0 to 1. So clearly, lesser than 0, fx will be 0. Fx will be 1 when small x, basically random variable, is between 0 and 1. So the probability of how this translates is the probability of getting landing anywhere between 0 and 1 is going to be 1 because these are the only available values, right? Moreover, fx is going to be 0 when x is greater than 1 because this is also not a option, right? Let's see more this graph. Now, if I say that the pointer lands anywhere between point A and B, A and B are the variables, right? So let's say A and B are both between 0 and 1. Then what is the probability? So we define the probability as the area of this graph. Okay, and by the way, this is a probability distribution graph. Okay, probability density distribution basically. And from there we can get the probability that the number or the point where it will fall will be between A and B. Again, probability of individual A and probability of B will be 0 because that's a property of the continuous random variable, right? So this is what they are saying here. The probability of getting number between A and B will be area under this shaded region. Moreover, the probability of getting exact outcome is 0. Where we already talked about this. Now, if some of you know, we have a random number generator that we have on a computer also. We have it on a calculator as well. So what the random number generator does is it creates a random number, let's say between any value. And if you give the threshold values of 0 and 1, it is going to generate a random number. So we think of it as a random number, but it's not random because it follows some algorithm in the computer which is there, right? So you can try it. I mean, once if you use Microsoft Excel, there we have a function for random between and the random values, and you can try it and get the samples, see the mean, and so on and so forth. So you can just try it once. Again, they're saying that it's not truly random because it's produced by some of the algorithm written inside the operating system. Now, generalizing the curve, we have the curve is, let's say, y is equal to fx, right? And this is called the probability density curve. Okay, why we are calling it as probability density instead of probability curve is because at any particular point the probability is going to be 0. We can just define the probability between 2 points. Okay, and that probability is going to be just the area under this curve. Let's say if we want to have the probability of getting a random variable value between A and B, it's going to be area under this curve for this. So this area, this will be the probability. Okay, so this is how we generalize the calculation of probabilities from the probability density curve. Okay, for a continuous random variable. Moving on. Moreover, taking it a step above. I mean, since it's a graph, right? We can take it to the integration instead of summation. We say that because the summation is not going to be simple. It's a complex curve, right? So we just say that if we had somehow the equation of this function, calculating the area under this curve would be very simple. It would be fx dx, where the limits would be from a to b, right? So this will be my probability of getting x between a and b. This, right? So this is an important formula when we are dealing with the continuous random variables. Moreover, all the probability distributions that we will see later that are occurring in the nature also, that are very useful for data science purposes, we will be using integral itself, because there may be limited cases where we have a discrete random variable. Right? We are going to discuss some of the discrete random variables today, covering the Bernoulli distributions and all. But these are very common, continuous. So this formula is very important. Also, let's try to see some of the properties from the above curve. I mean, from the last equation that we had, okay, from this probability density curve. Let's see some of its properties. The probability of any random variable is going to be greater than or equal to 0. Okay. Okay. Why I'm saying this is the probability, because you are referring to a probability density curve. You may not be able to define the probability at a particular point x, but it is going to be greater than 0. Otherwise, there is no point, right? Because the spinning pointer will also land at some point. So it will have a non-zero probability. We can't define it, but it will have a non-zero probability. Moreover, if we take an integral of the curve, the probability density curve, from let's say minus infinity to infinity, it's going to give me 1, because the sum of the probabilities is 1, as we already discussed, right? So and moreover, fx dx is the area under the curve, right? Minus infinity to plus infinity. That is going to be 1, which is the sum of the probability. Now, let's talk about the mean and variance of a continuous random variable. Uh, if we see at the mean, we had discussed earlier that mean is x into px, but that is modified here for a continuous random variable. It will be modified to x fx dx. Fx dx is equal to px, and you integrate it from minus infinity to infinity, then you get the mean. For a discrete, so right side would is displaying the discrete continuous variable. For a discrete variable, you had xpx, where you would sum it for all the x. Small x is basically all the values of a random variable capital X. And in discrete, we had the variance as x minus mu per square into px for all x. We would summate it for all x. The similar formula would translate to x minus mu square into fx dx. Basically, wherever you have px, you just replace by fx dx. And because it's a continuous random variable, you replace summation by integration. Okay, so these are very important formulas. You should remember this. Moreover, so this is a very famous chart that you will see. This is a normal distribution. You will see it occurring in the nature, right? So to give you an example, let's talk about the age that people live up to. Okay, so let's talk about India. Okay, I think the expected age in India is almost average age in India is almost 70 or something, maybe around 60. I mean, the range would be 60 to 70. So that expectation is your mean, right? 60 to 70 is your mean, but doesn't mean that nobody is going to live above 70, or everybody is going to live till 70. There are people who are above 100 as well, who are 150 or something, which are the outliers. There are people who die at very young age, 6 months, 10 months, and so on. So this expectation of the life that we are living, it also follows a normal curve. Who falls on this curve where is something which is not in our control. But what we know is that the whole population is going to follow this curve. So if you want to do this activity, you can go on some government website. They would have the mortality data. They would that would give you the age and all. And what once you try to plot it right, what you will see is this beautiful curve. And this bell curve, we also call it a bell curve. This you will see. I mean, very common in nature. This is the rule of the nature, I would say. Moreover, coming back to the technical things, right? So let's say for a distribution, you have a mean value of mu and a standard deviation of sigma. So what you know from here is the mean. Let's say for a bell curve, for the normal curve, mu lies in the between. Mu plus sigma, this value is mu plus sigma, mu minus sigma, and the area covered inside this will be 68%. 68% of the area will be in this side. So going back to the age example, let's say this point was 40 and this point is let's say 80. So we can say that people, at least 68% of the people have, I mean, they have lived an age, or they have completed 40 to 80 years of age, right? So that is common. Although for the age example, this mean may be different for different countries. For example, let's say if you talk about Europe or America, there the life expectancy is higher. So their mean may be higher, right? But they will also follow the normal curve. Moving on. Now, taking another example, let's look at a fair coin toss. Please note, we have a fair coin toss. Every example that we talk about for a dice or a fair, or a coin toss, it is going to be fair. Okay, we'll assume this. Now, let we define a random variable x, which is 1 if the coin comes up heads, and random variable x takes a value of 0 if tails comes up. Okay. Then we prepare the table where we have x, small x. Small x is the value of capital X. So small x 0, small x can be 0 or 1. The probability of getting small x is 0, which is uh, getting heads is 0.5 and getting tails is 0.0, 0.5 only. Now, again, with the earlier formulas, expectation of x. So this is a discrete random variable, right? We already know that the expectation for a discrete random variable is x px, right? So in this example, expectation of x is going to be x px, which is 0 into 0.5. So this will be equal to my one. Sorry, this should be a plus sign. Okay. So expectation of x is x px summated over all the values of random variable x, right? So once we do it, once we take the summation, we get as 0.5, right? So which is simple, right? I mean, if you toss a coin, what is the mean? Let's say in broader terms, if you had to say, what is the mean of getting ahead? I mean, if you describe an event as getting ahead is 0, getting a tail is 1, then on an average, 50% of the time you will get head, things like that. So all of them are related, right? So expectation of x is also coming out to 0.5. If we calculate variance from here, this will be x minus x bar square into px. So x is 0, mean is 0.5, 0 minus 0.5 the square into p0, plus 1 minus 0.5 square into p1, which will come out to be 0.25. And if you take the square root, right, and taking the square root of variance means standard deviation. Taking a square root, you will get a standard deviation of 0.5. So the expectation is 0.5 and the standard deviation is also 0.5. Right? So the extremum values automatically become 0 and 1. So we'll see that later maybe. Now, I want to introduce how do we combine the random variables. Okay. For this, let's start with an example of gambling game. Okay, you have $6 in your pocket, and you basically give them up to gambling. Okay, and you say, I will flip a coin. You will win $10 if the coin comes up heads, and $0 if tails, right? Then my winnings, if I calculate my winnings, so my winnings is also going to be a random variable, because it is dependent on an outcome of a random experiment. So my winnings are going to be 10x minus 6, right? Why 10x? Because my winnings are going to be $10, and I have already given up 6. So if I calculate my winnings, it's going to be 10x minus 6. If uh, if a head comes up, this x will be 1, and winning would be $4. Otherwise, if a tails come up, this would be 0, and we will be at a my winning will be minus 6, because I've already given up $6, right? So this will be the random variable. Now let's see. Let's try to calculate it mathematically. Is it a good bet or not? Now let's see the new variable that we have generated. We have created W, which is for my winnings. What are its mean and variance? Um, if you go by the formula, 10x minus 6, expectation is going to be linear. Expectation is always linear. So we have expectation of W as expectation of 10x minus 6. This expectation would be linearly applied to them. So it will be expectation of 10x minus expectation of 6. Expectation of 6 is going to be a fixed number, because 6 is fixed, right? It does not have a random variable. So it would give 6. And expectation of 10x, you can take out 10 uh, outside the brackets, and you will get 10 ex minus 6. So expectation of W will be 10 ex minus 6. Now you already know the expectation of x. X is just a coin toss, right? These are the values which x can take. Now this is going to be, if you substitute the value of 0.5 in here, expectation of W or expectation of your winnings is minus 1. So what does it mean? It means that it's a losing bet. How? Let's see how. Okay, when you win, you are getting $4 more, but when you lose, you are losing $6. Okay, let's say if you conduct this, if you let's say if this experiment is done twice. Okay, once you win and once you lose. You win $4, but you lose $6. You are at an average loss, right? So if you are bound to repeat this for, let's say, n number of times, 100 times, 1,000 times, you will observe that you are definitely going to be at loss, right? Which you have already calculated. The expectation of your winning is minus 1, right? Let's talk in terms of table, right? So this is the random variable x, which is just the coin toss. The outcomes are 0 and 1, and this is my winning random variable. If x is 0, this will be minus 6, right? X is 0, this will be minus 6. And if x is 1, this is going to be 4. Also, the probability of W will be 0.5 in both the cases, because probability of W will be equal to the probability of x, right? So you can also calculate the expectation of W from this. WPW, summation of WPW, you will add minus 6 into 0.5 plus 4 into 0.5. So that would again give you minus 1. Yeah, moving on. So in all, we conclude that it's a losing bet. If you want to do this as a homework, you can check with other values of your betting amount. Initially, it was $6, so you are at a loss. You can try to come up with a number, right? Let's say $4 or $5 or something, which will make you a winner in any case. Let's say if you try it for a large number of times. Now, coming back to the technical things, okay, leaving the betting ahead. Moreover, please don't engage in betting. It's not a very good thing. Once you get used to it, you will get used to it. So please stay away from it. So in general, we can show that expectation of ax plus b. X is my random variable. A and b are, let's say, some of the numbers, let's say 10 or 6. It will be equal to a into ax plus b, right? This is a very important formula. So we are saying that if we have derived different random variables from some other random variable, and if it's a linear combination, let's say ax plus b, then the expectation of that new random variable you can calculate via formulas, statistical formulas. You can just, take e inside. It will be expectation of ax, and since a is constant, you can take a outside, and then expectation of b will be b only because it's a fixed value, right? Basically numbers. Also, we can generalize it for the variance also. Sigma square of axb, which means variance of ax plus b, will be equal to variance of x into a square. Okay. Now you will say why we are missing the b term here. So this takes us back to the question: what is variance? So if you calculate the variance of a fixed variable, right, there won't be any. It would be zero because it's fixed. If it was a number 6, there won't be any variation. So it reduces to zero, and you can only see the term for your random variable. Right? So these are also important formulas. You should remember these. Moving on. Now, let's see how we can add two random variables together. Okay. For instance, we can think of tossing a coin twice. The number of heads on both tosses is x1 plus x2, right? X1 is the number of heads on first coin. X2 is the number of heads on second coin, right? So the final random variable that you are making is just a summation of these two random variables, x1, x2. Now, let's see for this x1, x2, what can be the possible values. Either you get no heads, which will be 0. Either you get head on any of them. In that case, x1 plus x2 will be 1. Either you get two heads, heads on both of them, it will be 2. And what will be the probabilities, corresponding probabilities? They will be 0.025, 0.5, and 0.25 again. Again, it's easy. If you calculate it this way, the expectation of x1 plus x2 is going to be 0 into 0.25 plus 1 into 0.5 plus 2 into 0.25. Moreover, once you calculate it this way, right, try calculating the other way. What is the expectation of x1? 0.5. What is the expectation of x2? 0.5. So expectation of x1 plus x2 is going to be 1. If we use this linearity formula, we get the answer in no time. Otherwise, we can take the longer approach. It doesn't matter. But if you have to be quicker, you need to remember this formula. That for linearity, we can just find the expectation of a linear combination of random variables, and we can take it inside basically, and all the constants will have an expectation 0. Also, sorry, all the constants will have an expectation equal to the constant, and the variance of the constant will be 0. Moving on. Now, let's draw the probability distributions of x1 and x2. Okay. So this graph is for x1. This graph is for x2. So this shows me the probability distribution, right? We simply have 0 to 1, it's 1, and 0 to 1, it should also be 1 here. If I talk about the x2, right, x1 plus x2, what is it going to be? This will be a graph like this, and it will take values 0, 1, and 2, and the area under this is going to be 1, because the total probability of any event cannot be greater than 1. The total has to be 1. Okay. So this is just I just wanted to show you if we combine the random variables, how the probability distributions work, how do they change for a combination of them. Moving on. Also, if we talk about the standard deviation or the variance, okay, not the standard deviation, just the variance. Variances are also additive for independent events. This is very important. The event should be independent. In that case, if the events are independent, their variances will also be linearly combined. Sigma square of x plus y will be sigma square of x plus sigma square y, which is variance of x plus y will be variance of x plus variance of y, given that x and y are independent. Also, in case of two coin tosses, when we are tossing two coins, they are obviously independent, right? There is no dependence amongst the two coin tosses. So the variance of x1 plus x2 is going to be a sum of individual variances, which is 0.25 that we saw earlier, plus 0.25, and it will be 0.5. So uh, this is very useful. The mean formula and the variance formula for the for a linear combination of random events. Okay, moving on. Now, if we want to generalize, let's say, to any sum of random variables, let's say three coin tosses, four coin tosses, and so on. So, what we say is expectation of expectation of sum of all the random events will be equal to sum of expectations of the individual random variable, right? This is just a generalization formula, the same continuation of what we just studied. Moreover, if they are all independent, then variance of the linear combination of xi's will be sum of variances of all xi's. So these are pretty important formulas. You should remember those. Moving on. Now, just a fact here, right? All of these calculations are very basic to the sampling theory of stats. Okay, you will see many summaries of the data, right? Sample mean, sample variations, where basically variances and all. They are they are actually linear combinations of the data. So, for example, if you take the one random variable as age of the person, and second random variable as uh, the what how can I say this? Second random variable can be your let's say uh, the age that they graduated and so on and so forth. So if you try with the linear combination, sorry, my bad. In this example, it won't be linear. Okay. So yeah, let me skip this example for now. Okay, we'll see it later. Now, we come on to distributions. We have already covered all the random variables. All right, how can we calculate the mean and the variance of all the random variables? Standard deviation is just the square root of the variance. Now let's see two distributions together. One is discrete and one is continuous. Right. Let's start with the discrete random variable, and let's see what are the distributions. We will begin with a discrete distribution, and we call it as a binomial random variable. This is a very important term that you will see, and you will get to know why we are calling it as a binomial random variable. Yeah. So binomial, as the name suggests, it has by means two outcomes, two basically, right? So whenever we have two outcomes of a random variable, it's a binomial random variable, right? So there is a random process which has just two possible outcomes, heads or tails in a coin toss, right? Win or lose in a football game, pass, fail, so and so forth. This is binomial random variable itself. Okay, so this is just an example of a scrap dealer saying that okay, your car has passed the smog test, so which is actually a success for her. It has failed the smog test, so it won't be scrapped. So we link it with the we call all of these trials as Bernoulli trial. Okay. So what is a Bernoulli trial? When we do repeat this experiment repeatedly, I mean n number of times, then it's called a Bernoulli trial, right? Let's say we toss a coin 1,000 times, 1 lakh times, and so on. Then it's a Bernoulli trial. Okay. Now, what are the properties of the Bernoulli trial? First property is that the result of each trial, it may be either a success or a failure. Okay. Basically, what we want to say is the probability is either going to be 0 or 1, right? The second property is the probability P of success is going to be the same in every trial. So if we talk about the coin toss example, the probability of getting a head is the same in every coin toss. Basically, first coin toss, you also have a probability of 0.5 of getting a head, so on so forth. In the 1,000th iteration or in the 1,000th coin toss, the probability of getting a head is going to be 0.5 only, it won't change. So this is the second property of the Bernoulli trial. The third property is that the trials are independent, right? When I say trials are independent, the first coin toss and the second coin toss are going to be independent. So that is the third property of the Bernoulli trial, right? So basically, we want to say that there will be no influence on the later outcomes. Also, let's say we start with a Bernoulli trial and the probability of success is P there. Okay. We build a new random variable by repeating this Bernoulli trial, and we call it the binomial random variable. Okay. So this term you will encounter many times when you will study the basics of statistics. Moreover, the distributions, the binomial random variable. Okay. Once we repeat the Bernoulli trial, we get binomial random variable. Now, let's define it as the number of successes in n repeated Bernoulli trials. Our random variable x, we are defining it as the number of successes in n repeated Bernoulli trials. Let's say we have tossed the coin n times. So x is the number of successes that we have. And when we say successes, let's say we have the number of time. Let's say we have heads coming up. Let's take a different example. Okay. In this one, we will talk about the binomial random variable. Okay. Once we have tossed the coin 2 times, and the binomial random variable here assumed is the number of heads coming up. So in that case, what are the possible what are the possible values the random variable x can take? It can be 0, 1, or 2, right? And what are the probabilities? For 0, it's 0.25. For 1, it will be 0.5. And for 2, it will be 0.25, right? So this is a binomial random variable. Let's see, is there a way to calculate the probabilities using mathematical things that we have studied already, basically permutations. So in general, the probability distribution of binomial for any probability p, right? So the probability is p of a success, and the number of trials that we are doing for this experiment is n, right? So the probability calculation will give the answer. How can we do it? Okay, uh, let's look at the formula first. The probability of obtaining k successes in n trials is probability x is equal to k is going to be nk. This thing here. Okay. this thing here is what we call combination, okay, which we have already studied in mathematics. NCK, this is NCK. This is just another representation of NCK. NCK into PK into 1 minus P to the power K into 1 minus P to the power N minus K. So this is the formula for getting K number of successes in any Bernoulli trial. When we repeat it, we get a binomial distribution, and this is the probability of getting K successes. So this formula is very important, and you should remember this formula for Bernoulli trials when they are repeated and we get a binomial, we take a binomial variable. So this is the probability of getting K successes. Now let's see how it, appeared, this formula. Let's say, as I already described, this representation nk with circular brackets, it is read as n choose k, nck. Okay, it's a similar thing as combination that we studied in permutation and combination, right? So this will be my binomial coefficient, and it is going to count all the possible ways of getting k successes in n trials, right? So, for example, your your every sequence of k successes is going to have k successes somewhere in between and f failures somewhere in between. Okay, the probability of a success is p, so automatically your probability of failure is going to be 1 minus p, right? This is understood. I mean, this is a given for Bernoulli trial. Now, for every success, the probability will be pk, p to the power k into 1 minus p to the power n minus k, because probabilities would be multiplicative in that case. For example, let's take this scenario. What will be the probability of all this scenario? It will be 1 minus p into p into p into 1 minus p into p, right? So that's why we could generalize it to, for any success combination, it would be k, p to the power k into p to 1 minus p to the power n minus k. So 1 minus p is my failure, right? Also, so in this scenario, you are getting 3 successes, as you can see in the picture. 3 successes. The success is at, let's say, second, third, and fourth place. But what if your successes were at first, second, third place? So you will have to have a different combination. So to account for that factor, your k successes can occur in n choose k ways. N choose k, it will be a number basically, right? So for example, if I say that out of 5, I have 3 successes, right? So it will be nc3, 5c3, or I can also write it as 5 choose 3, this representation. Okay, so what it would be is 5 into 4 upon 3 into 2. I hope you remember, right? So I mean, I think I'm missing something here. Yeah, it will be 3, one more 3 here. So your 3 and 3 get cancelled. It will be 20, right? So in here, the 3 successes, there are 20 combinations, right? So that's why in the previous formula that we studied, that's why we have this variable, this factor of n choose k, right? So I hope this is clear. Now, along with this, we have seen that what is the binomial coefficient for k number of successes. Okay. Now, since we have the binomial coefficient for any number of successes, we can plot the probability distribution as well. So we will cover it in the later sessions. Okay, but I will leave this with an example. Okay, if you remember, in the first session we were discussing about Demir, who is a who was a gambler, right? And he was trying to compare his two scenarios where once one die was being rolled and he wanted was rolled four times, he wanted the probability of six, and in the scenario two dice were rolled and he wanted to calculate the probability of double six in 24 rolls, right? So if you remember that example, I mean, you can refer to earlier sessions also, video or presentations, and try to think of what is the probability of rolling k6s in four rolls. Okay, you can use the formulas, it will be very easier that way, and try to calculate this probability. So we will conclude this session here. Okay, I hope it was informative. Any questions from anyone? Jatin, you are here, right? Okay, so okay, then let's wrap up the session. I will stop sharing.